as Miguel said, I don't really trust my Spanish to give the presentation in Spanish, so I'll do it in English, but feel free to stop me at any point and ask questions if anything is unclear or you have issues with what I'm saying. So as Miguel said, this work is about something which in a way is kind of standard, so the analysis of Bayesian models for cost-effectiveness evaluation, with a twist, with something which is slightly different, not necessarily usual in all the single case, which is the presence of structural zeros. So the fact that some individuals have a zero cost for some reason. So what I'll do in this talk is, first of all, to briefly go through the basics of health economic evaluation. And so I'm sure many of you will know about that. I won't spend too much time, so I'll talk about the objective. I'll say something about one of the main characteristics, which is that we have a multivariate outcome variable. And then I'll talk about the issue with non-normality of these variables. Then I'll move on and discuss in specific details the structural zero costs. So I'll just mention briefly what the existing methods are, and I'll discuss the proposed method that I have in this paper. And then I'll show you a quick example, which is about a trial about acupuncture. So I'll show you some results. I'll discuss a bit the issue of sensitivity to the model specification and how to actually implement this model. I've written an R package which goes with this paper, and it can be used to do the actual analysis. So, what's the objective of health economic evaluation? Well, the point is that we want to combine together two main dimensions of analysis: costs and benefits, clinical benefits, whatever defined, of some given intervention. So you may have a new drug, or not necessarily a drug intervention. It could be a complex intervention, behavioral change, anything really. But the point is that we will have some costs of implementation of a new intervention and some clinical benefits defined, for example, using some particular variable of outcome. We want to combine these two things so that we have a rational scheme for the allocation of scarce resources. In systems like the Spanish one, or the British, the Italian, where the government, the central government, pay for the provision of health, we do have some budget, and we have to apply this budget to the whole population. So we try and maximize the benefit that comes with the use of the resources that we have. Well, I say here recently, but it's a process that has been going on for quite a few years now. Models have become more and more complex. In fact, I think that the name health economics is some sort of a historical accident. It's called health economics because in the beginning, people like Mike Drummond at York University, who are economists, started to work in this field. But then the discipline has moved quite a lot, and statisticians have become a lot involved in the analysis of health economics. So I think, I don't know, I'm a statistician, so obviously I'm biased in this assessment, but I think that maybe health economics is kind of a branch of applied statistics. So anyway, nowadays we do models that are reasonably complex and reasonable to describe the problems that we have in health economics. And the point is that, in effect, we can frame the whole problem in terms of decision theory, which is exactly what we have to face in this case. We have a new intervention, and we want to see what are the potential consequences of applying this new intervention to some population. Obviously, this will happen in the future, so we have no uncertainty. We don't necessarily know all that there is to know about the cost and the benefits associated with each of these interventions that we are trying to compare. And therefore, rational decision-making is effected through the standard application of expected utilities, or the maximization of expected utility. In this area, the Bayesian framework is very much important and increasingly applied. I think maybe the first, not necessarily the first, but the big milestone, especially in the UK, was this report by David Spiegelhalter, who's one of the fathers of Wimbugs and one of the best-known Bayesian statisticians in the world, really. He wrote this report about the application of Bayesian method in health technology assessment and performance monitoring. And that was basically the prelude to the book that he wrote on clinical trials and Bayesian methods and the application in health. But there are many important scholars like Tony O'Hagan, who's now retired, but he was at Sheffield, Claxton and Scalfer at York, Giovanni Parmigiani, then at Johns Hopkins, now he's at Harvard, Simon Thompson at the MRC, Gordon Hazen, who's been working a lot on the expected value of information, and Northwestern University in Chicago. So many big names have worked in health economics under the Bayesian approach. And actually, I think it's interesting that probably more than in other areas, if you are Bayesian in health economics, you don't have to excuse yourself. You don't have to actually say, well, we're doing this analysis, which is kind of strange, because there may be some advantages. But normally people would do the frequentist analysis. I think in health economics is basically 50-50, if not slightly in favor of the Bayesian analysis, which, again, being a Bayesian statistician and therefore biased, is a very good thing for me. What is the main characteristic of cost-effectiveness models? The point is that, unlike many standard clinical analyses, we do have two outcomes, in effect, a bivariate outcome variable, because we have to deal with the costs, say C, and they can be specified in many different ways. We can talk about the direct or indirect costs. The direct costs, for example, are the costs associated with the acquisition of the new intervention. So if we're talking about some drug, it's the unit cost of the pill or the infusion or whatever the actual drug is made of. But also you have indirect costs, which may be costs associated with the application of the intervention, but not necessarily directly with the drug. So for example, if you have side effects and you have to go into hospital, then you accrue some additional costs for the health system, for the payer. There are other ways in which you can define the costs. These are called non-tangible, and for example, these may be societal costs. You all know these, I think, so I won't spend too much time. They're much more complex and therefore not often considered, but at least direct and indirect costs are always taken into account. In terms of the clinical outcomes, say E for, to give it a name, but it can be whatever we wanted to call. It can be a hard measurement, like the number of deaths or the occurrence of some events or survival rates, for example. But also it can be defined in terms of some utility measure, for example, the QALYs. And again, obviously, I'm assuming you're kind of familiar with these things, but if you're not, do stop me and I can talk a bit more. In any case, the point is that we do have these two variables that need to be taken into account. And typically, we cannot assume that these two things are independent. Of course, it would be much easier if you could say, well, let's just have two single univariate models, one for the costs and one for the benefits, and let's see what happens. But obviously, it's easy and straightforward to think that there must be some sort of correlation between costs and effectiveness. If a treatment is very much effective, then maybe it's been investigated with a new technology, with a lot of innovation in the last 20 years, so it will tend to have a higher unit cost, for example. So, for example, there will be that sort of positive correlation. Similarly, we may think that in most cases, if an intervention is very much effective, then it may reduce the overall cost, because maybe it costs you more to buy the unit cost of the pill, but then, for example, you don't have side effects, you don't have myocardial infarction along the line, so overall you save money. So again, there is some form of correlation between these two things. So statistically, the best thing we can do is for each individual, patient or subject I, to use some form of bivariate model. And the easiest way of dealing with this would be to apply a normal model. So EC would be a bivariate normal distribution. They would have a vector of means and a matrix of variance covariance. If you're a Bayesian, in this case, all these parameters would be random variables, and you would attach some probability distribution to describe this state of science, so what you actually know about them. Sometimes people abuse the Bayesian approach and use non-informative prior distributions, which are tricky and they need to be defined carefully. Sometimes people are fully Bayesian and they include some subjective knowledge or maybe knowledge coming from other studies or previous information. But in any case, we would have a probability distribution on these parameters. And typically, these would depend on the treatment being selected. So effectively, you would replicate this structure for treatment 1, treatment 2, treatment 3, and so on. However, we have a few problems in this setting, and the first one is that it is in general difficult to model bivariate data. We can do it, especially under a normal assumption, but it's easier to actually think in terms of some factorization. So whenever you have a bivariate distribution, you can always factorize as the product of some marginal distribution for one of the two terms and a conditional distribution for the other terms given the first one. So this is just standard probability theory. We can always do it. And it makes it easier because these two things are actually univariate. So they're easier to manipulate and to compute probabilities for. So for example, we may say that the effectiveness variable has a marginal distribution which is normal, depending on some parameters. And we could define a conditional distribution for the cost given the outcome in terms of effectiveness. And in this case, again, you would have a normal conditional distribution which is basically expressed in terms of a regression of costs on the outcome. However, we have another problem here, and that is that the assumption of joint or marginal conditional normality is often not realistic. We cannot apply it because the costs are usually skewed. Most of the times we have a few patients who have sort of a relatively low cost, and then just a fringe, a small proportion of patients who have a very high cost. Because, for example, they are the sickest patients, or they're very unlucky and they experience a lot of side effects, or, for example, they need to go into hospital and they have a particularly long length of stay for some reason. So they have a slightly higher cost, which increases the skewness of the distribution. Not to mention, of course, that costs cannot be negative. So you have a cost of some euros, pounds, dollars, whatever, but you can't go into the negative scale. So the assumption of normality is not very reasonable for the costs. And often, this is not normality for the effectiveness either, because sometimes they're just bounded between 0 and 1, like the QALYs or utility measures, for example. They may have skewness as well, so it becomes tricky to actually use the normal distribution. So some possible solutions are that you can transform the data, for example, taking the log of these distributions to make them more symmetrical and therefore more reasonably modeled using a normal. Or, especially if you're a Bayesian and you use a Bayesian approach, you may enjoy a bit more flexibility and therefore use suitable distributions like, for example, the gamma or the log normal distributions, or beta, if you are constrained to be between 0 and 1. And then apply, for example, MC estimation, which effectively allows you to use a more suitable distribution and not be constrained too much by the use of normal assumptions. A third problem is that sometimes when you have individual level data sets, for example, coming from a trial, some of the patients, for some reason, have a cost which is equal to 0. This may be, for example, because in the control arm, these guys don't actually access any of the health resources. So they don't have any actual active treatment, they don't have any hospitalization. So effectively, despite the fact that you can assume and observe an effective measures on these people, you don't have a cost. Their cost is actually set to 0. Sometimes that can happen also in the treatment arm. For example, you may have a study in which you're trying to investigate end of life. So these people may be very sick, they may have terminal cancer, so they enter the study, and even in the treatment arm, for example, they're supposed to take the treatment, but they die suddenly. So you can still measure some level of quality of life, for example, which typically will be very low because they're very sick. But you may not have access to the actual data for the costs because they haven't had time to actually experience it. So even in the treatment arm, you may have 0 for these costs. And the problem is that, for example, these models, the gamma or the log normal, are defined on a positive domain. The support of the variable is 0 excluded up to infinity. So technically, you cannot apply these models when you are faced with structural zeros. So a very simple solution is actually to say, well, let's just not waste too much time. Life's too short. Why don't we just add a very small constant to the whole data set? So effectively, we rescale everything from 0 excluded up to infinity, ideally. So in that case, you can apply a simple gamma or log normal model because you have a variable which is observed to be on a positive scale. So that's very easy. Unfortunately, it also potentially very problematic because the results are very much likely to be sensitive to the choice of this parameter epsilon, which you use to shift the data away from 0. And more importantly, you don't have a real guidance on how small these parameters should be. In some cases, you have the whole bunch of costs you have observed are really small, and therefore you need to add a very small quantity to move away from zero reasonably, but not to screw up the scale completely. Because ultimately you want to give a reasonable estimation of the average cost in the population. Sometimes, for example, in the case of cancer, you may have very large costs for many patients because there's a more serious disease, so they would have to go into hospital. The drugs are more costly anyway. So even an addition of 10 euros or 15 or 20 euros can be reasonably small enough, and it doesn't screw up very much your average estimation. But you just don't know that. There's no guidance. You can't actually define what number you should use in any case. So a more statistical approach is to use what I call hurdle models, which are, I think, very popular in econometrics as well. And basically, the point is to build some selection or mixture model for the probability of a given individual being associated with zero costs. So typically, you would do a logistic regression to estimate the chance that a random individual is actually associated with zero costs. And then, for those with a positive cost, you just fit the standard log normal or gamma model, and you estimate the average cost in terms of the mixture of the two components, those who have zero cost and those who have positive costs. In health economics, hurdle models have been used, but strangely enough, to the extent of my knowledge, they've not been used to perform a proper cost-effectiveness analysis, which means estimating jointly the costs and the effectiveness and then seeing which intervention is actually the optimal one. They've just been used to do some econometric analysis, which means, for example, to estimate the effect of some covariates on the actual costs, or to make prediction about the future costs, but never in conjunction with the actual estimation of the variable of benefit. So this is where I try and come in to extend the hurdle models to also account for the variable of effectiveness, of clinical benefit. So to extend this framework to allow to make a proper health economic evaluation or cost effectiveness evaluation. Is that clear enough? Kind of. Yeah? Cool. All right, so let me just put down the actual framework for my analysis. I suppose that I have a few interventions, say t interventions, 0, 1, 2, 3, up to t minus 1. And for each, I define the data as the union of these two different subsets. dt now is the data for the patients where I observe a zero cost, but also in dt now, I'm including the effectiveness variable. So there may be the case where somebody has a zero cost, but a quality of life measured in terms of 25 QALYs, say. dt pos is the remaining part of the data set where people are actually observed to have positive costs. Typically, dt pos will be much, much larger than dt null. I expect to have a small proportion of people with zero costs, although there are applied cases where you get up to 20% or something like that. So n is the total number of people in the data set if you sum across all the different treatments, and nt is the number of individuals in each treatment arm, and they are divided between those with zero costs and those with positive costs. At the very least, I'm assuming that D contains information about these two variables, the outcome, E and C. So some measure of effectiveness, again it could be a hard measurement, number of deaths, number of events, or some utility measure like QALYs, and the costs, including the zeros. Sometimes you have some J additional covariates, which I call ZTJ, to indicate the different treatment and the different covariate. And they are defined as well at the individual level. And these may be, for example, age, sex, comorbidities, baseline measurements, and so on. And notice that even if I am in the setting of an RCT, these variables are normally measured. Maybe they're not necessarily used in your final analysis because under randomization, these two things are balanced across, everything else is balanced across the population or the subgroup that you're analyzing. So you can do, for example, t-tests or ANOVA or anything else. But these variables are still measured and you can use them if you have them. To make life simpler, I'm just assuming that I have two interventions. This is not very restrictive though, because most of the times this is what we have. We have a standard treatment. For example, this would be what normally doctors are applying. And a new treatment, maybe a pharmaceutical company has developing is developing a new drug and they want to test it or to put it forward in the market, and I call this t equals 1. So I apologize for the choice of this green, which is not very easy to see. So what I'm saying here is selection model for c greater than 0. I should have used a different color, sorry. But this is kind of how the model would look like. So there are these three main blocks, the green, the red, and the blue one. And effectively what I'm trying to do is to connect them all together. So this would be the model that I use to estimate the probability that somebody has a zero cost. This is the red one, the model which I'm making to estimate the cost, still accounting for the fact that somebody has zeros. And the blue one is a model that I'm including in addition to the hurdle model, which is the red and green part, to estimate also the effectiveness variable. And I'll start by discussing this bit over here, which is actually quite simple, because effectively it's just a logistic regression. Okay, you don't have to do it as a logistic regression. You can use probit models. You can do anything you want, really. The point is that you do have an outcome variable in this case, which is a binary indicator. It takes value 1 if the observed individual has a zero cost, and 0 if they have a positive cost. And you can model it that way, so you have a logistic regression on the probability of a structural 0, depending on some intercept, and if you have them, some covariates. Notice that in this case, for two reasons, which I'll mention briefly, I'm using a centered version of the covariate. So for each covariate, I'm taking the original value minus the overall mean. So for example, if I have age, and my age is 40, and our mean age is 45, my value for the covariate would be 40 minus 45. I'm doing that for two reasons, as I said. The first one is that within the Bayesian framework, this helps convergence. And especially when I have a small data set or a small number of zeros, that can be a potential issue. So using the centered version of the covariates will make my MCNC algorithm run smoothly and converge directly. The second reason, I'll mention it later on. So if I'm a Bayesian, I need to define a model for these parameters, which I call beta t, depending on the treatment that I'm looking at. That's the intercept and all the other coefficients for the j covariates. One possibility, which doesn't have to be like that all the time, but the easy way of doing it is to assume a multivariate normal distribution, or actually I could even say IID distribution. So each beta is independent on the others, and they have a normal distribution with mean 0 and, for example, a large variance. Now, again, this doesn't have to be like that. This is just an easy convenience. And in fact, especially if I have a moderately large database, that doesn't really impact on the results, because the data will trump this prior, which is quite flat, and I will have an estimation which mainly is driven from the data. But you don't have to restrict yourself with this prior. In fact, if you don't have covariates, for example, or if you have a very small number of zeros, then you run into the potential problem of separation, which means that your estimations will be very unstable. They will tend to have a very large variance and therefore not be estimated with precision. So in this case, you can use a more robust prior. And in the literature, Gelman et al. Have suggested the use of this prior, a Cauchy distribution with a small scale parameter will basically stabilize the estimations, and therefore you end up with a better estimation of the variability associated with the coefficient. But again, I'm using this formulation with these two alternatives just for the sake of simplicity. You don't have to use that. In fact, you can change the prior and assume any prior that is relevant for your problem. You may have information about the actual input of these covariates, and therefore you may want to include that in some sense in the distributions. The second reason why I would use the centered version of the covariates is that because if these are centered, which means that they have a zero mean, then the average individual probability of zero cost can be calculated by rescaling the intercept of your problem. Using this formulation here. Now again, obviously there's no reason why we should only concentrate on the average individual, and subgroups may be really relevant in this case, because particularly when we're dealing with the issue of the zero costs, there may be a reason why some people have a zero. Maybe a particular subgroup of individual will have a higher chance of having zeros because they are sicker or because they are non-compliers or whatever. But in general, I can make my life easier and assume that I don't really, well, it's not true that I don't care about subgroup analysis. That's not my main outcome, for example. So if I have center covariates anyway, this PT is the individual probability of zero costs on the natural scale, and it's easy to compute as a function of the intercept. Of course, this model can be extended and made more appropriate to a specific problem. For example, you can include random effects or structure individual random effects if needs be. You can account for correlation over time or space if you have a multi-site trial, for example, and so on. So this is just a template model, but it can be extended whichever way is necessary. Right, so this parameter PT, which comes from what I have hidden here, so the selection model for the positive cost, will feed into the marginal model for C. In fact, I'm abusing the notation here. I'm talking about a marginal model, while in effect, this model for C depends on the value of D, of the indicator for structural zeros. But it's marginal with respect to the cost, to the benefit variable. So this parameter PT will feed into this model, which I'll now go and describe, and basically allows me to link it with the selection process. So what's the objective in this case? I want to specify one single distribution for both the components of the mixture. I said that I have two groups in the variables of cost. I have those people who have zero cost, which I know are kind of particular and different from the others, and I have a group of people with positive costs. But still, I want to use one single distributional assumption for both of them. And the way in which I do that is to actually move the differentiation into the parameters. So basically, I'm just saying that there's a common family of distributions P for the costs, but depending on the value of the indicator, so this is for the patients with null cost, with zero cost, and this is for the patients with positive costs, I have a different set of parameters. So effectively, all I'm doing is indexing the distributions using different sets of parameters that allow me to differentiate among the two groups. So what I will do is to define theta null in a way that that distribution will give me an estimation for the cost of 0, because that's what I want, that's what I observe. These guys have 0 cost, so I want to estimate their average cost as 0. And also I allow for a formulation of a theta pose to have some suitable distribution, for example a gamma or a log normal or whatever I want, but so that these guys are allowed to have a positive cost. And at this stage, I can choose any formulation for this distribution. As I said, it can be gamma log normal because these are the clear, easy example to deal with, but it can be anything. If you find a different distribution or a mixture of distributions, you can still apply that. The main point, which I should actually stress, is that in this way I have just one single distribution. I'll show that later on. And that is very helpful because with one command, effectively, I can code both members of this mixture distribution. And that is very effective in terms of my MC algorithm. So while using up some parameters which I don't necessarily need with this bit here, I actually make my life much easier, and I gain something in effectiveness when I run my MC algorithm. So that's good. So let me show you what happens if you, for example, wanted to model the costs using a gamma distribution. Effectively, what I'll do is to use this formulation. Now, here I have a nested index. This is the parameter eta t, dit. So because this variable takes values 0 and 1, effectively, I have these parameters as a pair of numbers. So theta pos will be eta t0 and lambda t0, where this is the shape and this is the rate of the gamma distribution. When d is equal to 1, I will have the parameters for the null distribution, for the degenerate distribution, which will be exactly equal to 0. And I'll call them eta t1 and lambda t1. T, in this case, remember, indexes the treatment. So in my case, I have t equals 0, the standard treatment, and t equal 1, the new treatment. By definition, as I said, these two parameters are the shape and the rate of the gamma distribution. But also, I can link them to the actual parameters in the natural scale. For example, the mean and the standard deviation of the cost distribution. And I have these two formula here. So these psi ts for each treatment and for each member of the mixture is the mean on the natural scale. And this zeta ts is actually the standard deviation of the costs on the natural scale. So effectively I have a one-to-one relationship. Once I have defined eta and lambda, I know what the mean and standard deviation of the cost will be. So the way in which I have to model my data is to allow these two properties. Case A, I have to have that the mean and the standard deviation of the cost are 0, because for those people, that's what I observe and that's what I want to recreate. For the other group of people, what I call B, I want to allow for the fact that these two numbers should be positive. I want to estimate a cost as a positive number, because this is what the data are telling me, with some positive variance, because again, that's what the data are telling me. So I will have a non-degenerate distribution in the set of individuals with positive costs. It's very easy to achieve part A. I just need to be a bit clever and use a very simple and very informative prior distribution in this case. For example, if I set the shape parameter equal to some value little w and the rate parameter equal to some value capital value, assuming that little w is much less than capital W, then by definition this would be the mean, and it would be the ratio of a small number divided by a very large number, which goes to 0. And also the standard deviation will be the ratio of these two numbers where the denominator is squared, which means that the variance or the standard deviation will go to 0 at an even faster rate. So for some reasonable selection of these two numbers, I will have that under this framework, the mean and the standard deviation in the natural scale are actually 0. So I have a very informative prior that tells me that the costs for this group of people will be estimated to be 0 no matter what the data are. And incidentally, the data will be 0, 0, 0, 0, so it will all be consistent. For the people in the positive costs, I could apply some prior distribution for the rate and the shape parameters. But actually, it's much easier to work with the natural scale parameters, so the mean and the standard deviation. And for example, I could say, well, let's just encode some assumption about the mean and the standard deviation in terms of uniform distribution. Again, I could use these things, but I don't have to. I can have any information I want, and I can model these two things in any way I want. This, again, is just an easy way to do it. But the main point is that once you have defined a prior distribution on the mean and the population standard deviation of the costs, because of the relationship that I showed you earlier on, these two things basically, you will imply a prior for the rate and a prior for the shape. So you're done. Once you have included these two prior distributions, you will have a prior for the natural parameters of the gamma distribution. In general, these things will be quite informative. Even if these uniform prior are reasonably vague, you will include a lot of information on the rate and the scale. But that doesn't matter. The point is you want to be vague or informative on the natural scale. Whatever happens to the rate and the shape, as long as it is consistent, is okay. So we're happy with that. Very quickly, you can do a similar reasoning for the log normal distribution. Again, I have this nested index. In this case, these natural parameters are just the population average and the standard deviation on the log scale, by definition of the log normal distribution. But again, I do have a closed form expression to transform these parameters to the natural scale, to the average and standard deviation of the costs rather than the log costs. So again, I can set these two parameters, eta and lambda, to some values so that the prior is really strong, and for the people with 0 costs, the estimation will be invariably 0, which is what I want. And again, I can allow some prior distribution on the mean and the standard deviation in the natural scale, so that some prior will be induced for these two things over here. And again, as long as I have the right prior information on the natural scale, it doesn't matter what happens on the log scale. The point is, it will be consistent, so that's fine. So regardless on the actual model I'm using, whether it's gamma or log normal or anything else, once I have estimated these two means, and remember this number here, psi t1 will be 0 by definition. I'm using to estimate this a prior distribution which is 0 mean and 0 variance. Therefore, no matter what the data are, I will estimate the mean and the standard deviation to be 0. So I can use these two numbers to calculate the overall average in the population as a mixture of the two components. So this is the chance of being a 0 cost multiplied by 0, which therefore cancels out. This is the chance of having a positive cost times the mean of the patients with positive costs. And this would be effectively down-weighting the average in the population using the chance of being a positive cost. So I'm actually done in that sense. I have estimated the cost in the population, accounting for the fact that some people, for some reason, have 0 costs. The next thing would be to use these two numbers, so the average estimation of the cost and the actual individual cost that I have observed, including the zeros, in a regression setting to estimate the population average measure of effectiveness. And therefore, I can use these two things, the mean of the cost and the mean of the effectiveness in each treatment, to actually perform the health economic analysis. This is what I need for the health economic analysis. So what I'll do is, again, to use a conditional model on the effectiveness, because I will condition on the cost. I will use a regression setting like that, for example. This phi IT will be the individual conditional average effectiveness, which will depend on some overall effectiveness in each treatment group, and it will be a function of the costs. Of course, I could have other covariates here. I could extend this model and put some more covariates, for example, again, sex and age and whatever else. But I don't have to. This is a minimal requirement for the model. The last thing I need to do, if this transformation G is not the identity, is to rescale the overall population average effectiveness, which I can just simply do by applying the inverse transformation G to the -1. And therefore, I will have an estimation of the overall average effectiveness in the population, which depends on the costs, of course. So I will account in the estimation of the effectiveness for the fact that some people will have a 0 cost, and there may be a reason why that is. Let me show you a quick example, and I'm getting closer to the end of this talk. The data I have, in fact, I've managed to get more data, which are more interesting, but for the sake of the example, I'm just using this original one, which are much easier. It was an RCT in the UK primary care setting, and the objective was to evaluate the cost effectiveness of some intervention, which was adding acupuncture sessions to some usual care in the management of headache. So T equals 0 is just usual care. If you had a headache, you go to a doctor and they'll give you maybe some pills, or they'll massage you or do whatever they do. Treatment T equals 1, they also added some 12 sessions of acupuncture to see whether that makes a difference. The measure of effectiveness is the total QALYs gained. So there's a questionnaire, the EQ5D in this specific case, I think that was it, which is used to estimate the level of quality of life for a given patient under a given intervention. Only a subset of the original database had valid data, and this is what I'm using. So I have 119 patients in the control group and 136 patients in the active treatment group. Because the annual time horizon is selected, so basically these guys were measured at a year of observation or follow-up, basically, then the QALYs are included in the interval 0-1. The QALYs are a measure of quality-adjusted life year. So in a year, you can only gather 1 year of life, or less, if you're not living at the full health. So the QALYs, my effectiveness measure, lies between 0 and 1. The overall cost is calculated by adding up all the several components, and they are non-prescription drugs, visits to private health care, the visit to the guys who are delivering the acupuncture intervention, drugs, prescription, and so on. So, in any case, I do have my data set made by these two variables, E, which is the total QALY, a number between 0 and 1, and C, the total cost associated to each of these patients. And that includes whether they go to the acupuncture or not, whether they go to the doctor, whether they get pills or anything. So, briefly, I specify my model in terms of the selection model. This is an indicator variable, as I said. because I don't have covariates, I'm using a robust formulation here. I only have the intercept, and to avoid problems with the estimation, I'm using the robust form of the Cauchy distribution. Now, of course, this is a big limitation of this example. There's no reason why we should assume that there's no other variable that can explain the zero mechanisms. I'll come back to that later when I'll try to make some links with the missing data literature. But obviously, I'm aware that in a real analysis, this would not be enough. And I'll say something more about that, but bear with me for a second. I've tried both models, the gamma and the log normal specification for the costs, and I've selected these values of the parameters W and capital W so that I'm ensuring that in the null group, the cost is actually estimated to be 0. I've also done some sensitivity analysis, which I'll mention on these two values. And for the qualis, the effectiveness, because this measure is between 0 and 1, is a continuous number, I'm using a standard beta regression, which means that I model these data as beta as a function of these two parameters. This is the conditional mean, this is the conditional precision, well, this is the precision. I have this formulation, and I give minimally informative normal distributions on these parameters. Again, this is just an example, and in real life, you may want to have better distributions to include information, to have meta-regressions, for example, and use data from other studies that can tell you something about these parameters. You can do all that. You should do all that. In this case, I'm just making life easier. Of course, the overall population average effect is calculated by the inverse logic transformation of this parameter, which is the intercept of this regression model, and therefore I get that number here. So, these are some results. Among the other things, what we can do for each of the two specifications, this is the gamma beta, gamma for the costs and beta for the effectiveness. This is log normal beta model. I can estimate for the two groups, this is the control group, and this is the active intervention group. I can estimate the chance of having a 0, which is pretty much the same in both models, and it's about 4%. And I can do the same for the active treatment, where the proportion of 0 is much lower, is about 1%. And also I can estimate the cost components for the cost which is non-zero. And then the average cost, which will be lower than this one, because it's down-weighted by the fact that I have a proportion of people with a 0 cost, and the average measure of effectiveness. Now, these two estimations are kind of very similar in both models. The estimation of the cost is actually very much affected by the model that I am selecting. And that is reasonable. We're using different specification for the sampling variability. The log normal and the gamma model react in different ways. And therefore, I have a different value estimated for the cost. I have, for example, £403 here and only £378 here. That's okay. It doesn't depend on the framework I'm talking about. It depends on the choice of the actual distribution. So, for example, you could do some model average here to say, I want to account for both uncertainty in these two models, because I don't really know whether it's a log normal or a gamma distribution. You may do simpler analysis and, for example, do some quantile plots and see which of the two fits better the data and so on. But the point is, this is not a problem. This is just a feature of using different distributions to fit your data. Interestingly, though, if you actually go on and do the health economic analysis, I'll explain these graphs in a second, the point is that there is no real effect, there is no real impact in the choice of these two things. The estimation of the cost is actually different and off by about £20 on average, but the decision that you make is that the acupuncture is actually a cost-effective intervention. And this is because the ISA, the incremental cost-effectiveness ratio, is actually quite small. It's about £8,000 for the gamma beta model, and about, sorry, you can't actually see it, is about £9,500 for the log normal beta model. In the UK, NICE say that if you have an ISA which is less than £25,000, then you're okay. The treatment is cost effective. So in either case, I wouldn't really have a problem in deciding which intervention is the most cost effective. Of course, if I did have differences, and for example, this model gave me an ISA of £24,000, and this model gave me an ISA of £28,000, then I would have a problem, because I wouldn't know what to choose, and I would need to do something more. But in this case, it doesn't really matter, basically, because both models are telling me the same answer. These three things, actually, this thing here, the expected incremental benefit, is a measure of the optimal decision in terms of the willingness to pay threshold. And basically, you say that for all the values of the willingness to pay for which this line is positive, then treatment 1 is more cost effective because it has the highest expected utility. So if you're willing to at least allocate £8,300 for the new treatment, then it's more cost effective. And similarly, you have some value here. This thing here is the cost effectiveness plane, and all these points are a measure of variability of your analysis in terms of the parameter uncertainty. So each point effectively represents one possible future outcome in terms of costs and benefits. And what you want to see is that most points are actually in the area of sustainability, which is where this gray shaded area is. I don't know if you can see it, but basically below the line of the maximum threshold selected by the decision maker, which is nice in this case, and it's £25,000. These two things are used to make probabilistic sensitivity analysis. I won't go into the details. I guess most of you will be familiar with them. If not, we can come back and you can ask me questions. But the point is, again, these two things will tell me that in addition to acupuncture being the best optimal decision solution, also there isn't a lot of uncertainty about this solution. So I would choose acupuncture with no real great uncertainty. The second point I wanted to make is that, as I said, I've done some sensitivity analysis to the value of these parameters, capital W. So the thing that I'm using to make sure that in the null population the cost is actually estimated to be 0. Now, these are the estimation for the gamma model and the log normal model. This is the estimation for the cost in the average cost in the control group. These are the estimation of the costs in the active treatment group. In this particular graph, I've set the value of little w to 1, and I have varied the value of capital 1 from 10, 100, 1,000, 10,000, 100,000. And as you can see, obviously there are differences in the two models. The gamma and log normal model will have different values, and we've seen that, and that's okay. That's the way in which they function. But the point is, all the estimations, for example, all these red graphs and all these blue graphs are the same. They don't depend on the value that I'm assuming here for W. So the procedure is very much robust. It doesn't matter which value you choose as long as they are reasonable values so that the mean and the standard deviation go to 0 in that particular subgroup of the distribution. Then your estimation will be the same not only on average but also in terms of the variability. So that's fine. You don't have to worry about robustness in a sense. You know that this model will be robust in that respect. So which way you choose, you know that you will be estimating the cost in a correct way. There's another thing I need to mention before I wrap up, is that while this does not have an implication in the estimation of the costs, and therefore in the health economic evaluation, it does have an effect in model fitting. So for example, if you're using things like the DIC to measure how well a model is doing to fit your data, then the choice of the parameter W will make a difference. And again, that kind of makes sense because that W defines how quickly you go to 0 in the population for which you want to have an estimation of exactly 0. So if you have a very large value for W, which means that you go to 0 very, very quickly, then your model fit will be better. And the DIC will be much smaller, for example. So this will give you differences, and it's something that you need to be careful and think about. But the good thing is that this is not relevant at all for your economic evaluation. It doesn't matter at all. Your economic evaluation will be robust. So that's a good thing. If I have 2 more minutes, yeah. I wanted to make a link to the missing data framework. Maybe some of you are familiar with missing data and how we treat them in statistics. You know the thing with the mechanisms that you can define. So the easiest one is missing completely at random, which means that you assume that when you see a missing, it doesn't depend on anything else. It's just completely random. Maybe because somebody dropped, by chance, a beaker in a laboratory and therefore you don't have the observation on that value for that particular drug. or for whatever reason, there's no real mechanism that differentiates the missing from the observed data. Obviously, that would be great, because in that case, you don't really need to worry about the missing, but it never happens in real life. If you have a missing in real life, that's because there's a reason for that. The next best thing is to assume missing at random, which means that if you can observe some other covariates, then these are enough to explain away the reason why you have a missing in your data. And because you can observe them, you can control for them, and you can make an unbiased analysis. That's good enough, but not always reasonable. Sometimes you are to face the situation of missing not at random, which means that there's something that decides why I am a missing value and Francisco isn't. And we don't necessarily know what is this thing that defines my process for being a missing data. Here there's something similar going on. It's not quite the same. But the point is, if you look at the green square here, when I was saying earlier on that I didn't have covariates, effectively I was assuming that there's nothing that I don't observe that matters to explain why somebody has a zero cost. And this is nonsense, basically. If somebody has a zero cost, there must be a reason why. As I said, probably they are sickest, so they are much worse off. They have baseline characteristics that make them more likely to die early, for example, and therefore to not have any cost. Or maybe there's a reason because the site where they are observed is actually not a very good site, and they're not good at reporting the costs. So, in fact, to assume that the covariates are not important and to do the analysis like I've done, just because I didn't have the covariates in that example, is not the best thing to do. Effectively, I was assuming some form of Z-car, so zero completely at random. The zero are not necessarily completely at random. If you have some covariates and you observe them, then you have a parallel thing with the zero at random, given some information that you can observe. But there's no reason to rule out the possibility that the zero is actually not at random, and there are things that you don't measure that would explain why some individual patients have a zero cost. Now, this framework in itself, in its version, in its standard version, cannot cope with that. It's you who have to decide and say, I think this is zero completely at random and I don't have covariates. Or, I think this is zero at random and I'm including sex and age and comorbidities, and that's enough to explain away the zero mechanism. But the point is, you can extend the model very easily in, for example, using econometric techniques like instrumental variables or things like that to account for the fact that you may have non-at-random mechanisms. So I think this is a nice parallel with some other areas of statistical analysis. Although, as I said, there are some technicalities whereby they're not exactly the same thing. They're similar, but not quite the same. Just a couple more things. The first one is that there is a package that accompanies the paper. It's called BCES0, which stands for Bayesian Cost Effectiveness with Structural Zeros. It's freely downloadable from CRAN, and there is some documentation on this website. And the point is that when you download the package, you have some data, and you need to decide the distributional assumption for the cost. And at the moment, these three are implemented. So you can say that the costs are gamma, log normal, or normal. You specify the distributional assumption for the benefits, and I have four possibilities. You can say that the effectiveness is gamma, beta, binomial, or normal. A list with the data, some other options, and you can find information here on how to do it. And then what the package will do is to write a TXT file with the bugs model. So that would just be a template, in fact. You don't need to use it as if it's the right model, but at least it saves you from actually starting from scratch. This file will be saved on your computer, and you can then access it, modify it, for example, include more covariates, specify random effects, change the prior distributions. But again, you do have something to be used as a template to develop the more complex analysis and to put more stuff in it if you want. So I think that's a nice thing of this package. If you're happy with the basic framework, then it will also do all the analysis for you. It will calculate the estimation of the posterior distributions, and then you can also use another package which is called BCEA, and I realize this is a shameless piece of marketing which I'm doing, and I apologize for that. BCEA stands for Bayesian Cost Effectiveness Analysis, is a package that I have written to accompany this wonderful book which I wrote. And the point is that I think BCA is actually not a very clever package. All it does is to standardize the process of post-processing of health economic data. So you have to be clever and define your own model. And you can be frequentist, although we'd rather you be in a Bayesian, but you can be frequentist and do all the simulations using Bootstrap, for example. You can be Bayesian and specify your model with MCMC and do your simulations. Once you are at that point, BCA comes into your help, and actually it will do all these graphs that I was showing earlier on. So it will calculate the cost-effectiveness plane, cost-effectiveness curve. It will tell you the value at which you have the optimal decision, and so on. So it's just a matter of standardizing the post-processing of health economics. You have some links here. There's more discussion and examples and things like that that are discussed in the book as well. And then the final thing I wanted to mention, and again it's very much shameless marketing in a way, there's this thing which is called Base Pharma. It's a workshop which we organize yearly. I've been involved in the last 4 editions, and I think it's actually a very good thing. For the last 2 years it's been the best conference I've been to. And next year we will be held in London. I've been basically tricked into organizing it. And there will be some information available on this website. And I think you can ask Miguel, and he'll say it was great. And thank you very much for that. Muchas gracias.